Suppose we have a matrix A and it's a square matrix. Okay, suppose we have a square matrix A, then the determinant of A minus lambda I will give a polynomial, right? And this I here is the matrix of same order. If this matrix A is of order n cross n, then this I will be of n cross n order. Okay, so this polynomial, when we calculate the determinant of this matrix A minus lambda I, it will give a polynomial in lambda, and this polynomial is known as characteristic polynomial. Of matrix A. Okay, Cayley Hamilton theorem. This theorem says that if the CH of characteristic polynomial of matrix A is something like P of lambda, then this matrix A will satisfy P of A equals to 0. So when we replace lambda by A, then Cayley Hamilton theorem says that the characteristic polynomial of A will be equals to 0, and this equation will be satisfied. Okay, so basically this P of lambda here is characteristic polynomial of A, and when we replace lambda by A, this equation here is satisfied. That is what Cayley Hamilton theorem says. It is interesting to know that the roots of characteristic polynomial are eigenvalues of matrix A, right? There is another term is there, that is minimal polynomial. It is nothing but a monic polynomial of smallest order, smallest degree, which satisfies so if the monic polynomial is m of x, then it satisfies m of a equals to 0. So when we replace x by a, it should give 0, where a is the matrix and ma of x is a minimal polynomial of A. Suppose A is a matrix and we want to calculate the characteristic polynomial. So first we'll find a minus lambda I, that will be equals to, and this will give 4 minus lambda 3 2 1 minus lambda, right? Now to find the characteristic polynomial, we need to find the determinant of this matrix, right? So determinant of this matrix of lambda I, a minus lambda I, will give us 4 minus lambda multiplied by 1 minus lambda minus 2 into 3, right? What it will become? And it will give lambda square minus 5 lambda minus 2. So this will be the characteristic polynomial of matrix A. Okay. And this can be P of lambda is equals to lambda square minus 5 lambda minus 2. Our Cayley Hamilton theorem says that this P lambda equals to 0 should be satisfied by A. Actually, in formal sense, what Cayley Hamilton theorem says that every square matrix satisfies its characteristic polynomial. So if A is a square matrix, it will definitely satisfy this characteristic equation. So it means that PA will be equals to 0. Okay. So if you want to see whether it is equals to 0 or not, we can place A in place of lambda, right? So our P lambda equals to lambda square minus 5 lambda minus 2, and when we place A in place of lambda, then it will become A square minus 5 A minus 2, and we know that our A is 4 3 2 1. Here A is equals to 4 3 2 1, so A square will be equals to 4 3 2 1 multiplied by 4 3 2 1. It will give 22 15 10 and 7, and when we put A square as this, A as this, our matrix, and this constant 2 is multiplied by I. So when you apply Cayley Hamilton theorem, always remember that when the polynomial is like this, okay, and you have a constant in the polynomial, that constant itself gets multiplied by an identity matrix. Okay, so hence we have our characteristic polynomial with A in place of lambda and constant multiplied by identity matrix of same order of A. Then we have, this is A square here, this is 5 multiplied by A, and this is 2I, and you can say it equals to 0. Hence, if you have any square matrix and you find characteristic polynomial of that square matrix, you equate that characteristic polynomial as with 0, then this characteristic equation will satisfied by the matrix A. That is the Cayley Hamilton theorem.